That rock here with some math. Let's graph trig functions when there's a coefficient to the input. Okay, so what I'm going to do is first remind us how to graph cosine x. So we're first going to graph this function here. And then we're going to graph a cosine function when there's a coefficient to the input variable. We call that coefficient the frequency. You'll see why. Now, I'm going to graph just cosine. I'm going to remind us what it means to graph cosine. So remember what it means, what cosine's definition is. If we have an angle in standard position that intersects the unit circle at some point, like a 0-degree angle would intersect at 1, 0, a pi halves radians angle would intersect at 0, 1. Then you put in the angle measurement and you get out the x-coordinate of the intersection point where the angle intersects the unit circle. So cosine of pi halves is equal to 0 because a pi halves radian angle intersects the circle right there at 0, 1. Whereas cosine of 0 is equal to 1 because a 0-degree angle doesn't rotate at all. So the terminal side's right there. The intersection point is that point. See where the intersection of the circle and the angle is, would be 1, 0, and the x-coordinate of that intersection is 1, therefore cosine of 0 is 1. You put in the angle, you get out the x-coordinate of the intersection point. All right, now that we've reviewed the definition, we know that the x-coordinates are the important outputs when you put in inputs that are angle measurements. So the important outputs, if I just went by every pi halves, so 0 is 1, pi halves is 0, another pi halves which gets me to pi would be -1, another pi halves which gets me to 3 pi halves would be 0, and another pi halves which gets me to 2 pi radians is back to 1. And then it would keep repeating. At 5 pi halves it'd be back to 0. And then at 3 pi it'd be back to -1, and at 7 pi halves back to 0. It just keeps repeating itself. It's called a periodic function. So we're ready to graph now. Thinking of that, let's see if I can get both diagrams in the screen where y'all can still see it. So we can see that diagram over there, and we're going to come over here. And in this diagram, x is representing the inputs. So x is representing the angle measurements, the theta values, whereas the outputs, y, is representing the outputs, which remember are the x coordinates. So that's confusing. Y is x. So you just remember, over here in this diagram, x is inputs, y are outputs. In this diagram, theta are the inputs, the angle measurements, and the x-coordinate are the outputs. Okay, so we're ready to graph. When the angle is 0, the output is 1. So we put a point at 1. Because when the input was 0, the output was 1, so at 0, 1. Okay? At pi halves, the output was 0. When the angle was pi halves, the output was 0. So when the input is pi halves, the output is 0. At pi, the output's going to be -1 because here at pi, the output is -1. At 3 pi halves, it's back to 0. At 2 pi, it's back to 1. And then it repeats itself, so at the next pi halves, which every 2 tick marks is, it's going to come back to here. So, and remember, these things are curves. They don't make linear lines. So it's a curve that looks like so. And the 3 dots represents it. It's going to keep repeating. It will keep repeating on this side as well. So it'll hit right there, because that would be negative pi halves. And negative pi halves over here in this diagram would rotate this way and sure enough land there where it's 0. So that is your cosine wave right there. Now what we want to do different is graph, and I'll do it in blue, cosine of 2x. Well, notice what happens when I put 0 in. 2 times 0 is still cosine of 0, which would still be 1. So I still have a point there. Okay? But what happens if I put in pi halves? Cosine of 2 times pi halves. Oh, well, you double a half a pi, you get a full pi, because those reduce. And cosine of pi, remember, is -1. So when I put in pi halves, I get cosine of pi, which is -1. So at pi halves, it's -1. Wait, we got to this point really early. In fact, we got there halfway, okay? So let's back up and do pi fourths. I didn't label this, but this tick mark would be pi fourths because it's half of pi halves, okay? Let's back up and do that. Let's put in pi fourths. So cosine of 2 times the input is going to be pi fourths this time. Well, if you double fourths, we all know you get halves. So if I have pi fourths and I double it, I'm going to get pi halves. So this is going to be pi halves. And cosine of pi halves is the x-coordinate 0. So if you put in pi fourths, it turns into cos of pi halves, which is an output of 0. So at pi fourths, I have the 0. So this point came here. So what's happening is all the points are being dilated in by a factor of 2. So this point, if you cut pi in half, you get pi halves. So this point came under pi halves. This point, if you cut pi halves in half, you get pi fourths. So this point of 0 came to pi fourths. Okay? And so they're just all getting cut in half. So that means that it's going to look like this. This 2 pi is where it was 1, but remember, cut 2 pi in half, you get pi, so that's going to be where it's 1. So notice we have a full cycle. That's a full cycle of the cosine wave in half the time. No coincidence. If the frequency is 2, your period, which is the length of the input domain that it takes to complete a cycle, your period gets cut in half. So if the frequency is 2, the period's going to get cut in half. If the frequency is 4, the period's going to be divided by 4. And that means the reason why this is called frequency is, since I'm already done, I'm going to repeat myself. Well, every pi fourths, we have one of the key points. I get a 0, and then another pi fourths at -1, another pi fourths I get a 0, another pi fourths I'm back to 1. And so notice that, whoops, sounds a little messy, but it's okay. Notice I have how many cosine waves? There is 1, and here is a second one. So we have, over the usual period, usually when you just graph in cosine of x, the period is 2 pi. That's the length of the domain that you need to graph one cycle, is 2 pi if you're graphing a normal cosine wave. But when the frequency is 2, over that same period, you're going to get 2 cosine waves. So the frequency of the wave is doubled, and that's why we call this coefficient the frequency. So you use the frequency to know how many cosine waves you should see over the usual period. But you can, if you just want to graph one cycle, you can use the fact that you're going to scale down the usual period by a factor of the frequency. We're going to call that the squeeze box theorem. So let me lift this up and let's write down the squeeze box theorem. Why are we calling it the squeeze box? Well, do you know what squeeze box is? It's a slang term for the instrument, an accordion. An accordion is the instrument with the folds in the middle that you squeeze back and forth. And when you squeeze it in, the folds become more frequent over a shorter period of time. And when you pull it back out, they become more stretched out, less frequent over the period of time. And so what we did to the black curve is we squeezed it in so we had more folds. So that's why I call it the squeeze box theorem. And then what the squeeze box theorem says, okay, I haven't proved it by any means, but I've demonstrated it, is that the period of y equals any trig function that has some coefficient here, call the coefficient maybe f for frequency, okay, will be equal to the usual period when there is no coefficient. The usual period when there is no coefficient. Let's see, can we see all this in the screen? Yep. Okay, maybe need, okay. And divided by the frequency number, the frequency factor, the coefficient to the x on the input. So this tells you the new period. So if we do it for the period of y equals cosine of 2x, well, the usual period of cosine and of sine and of their reciprocals is 2 pi. The usual period for tangent and cotangent is just 1 pi because it doesn't involve the radius. It just, the definition of tangent and cotangent just involve y and x, so it's just 1 pi. But the definition of sine, cosine, and their reciprocals, secant and cosecant, is 2 pi. So the usual period for cosine is 2 pi, and then I put this 2 down here, those reduce, and so it's pi. So the period of y equals cosine of 2x is just pi. And then if we go back and we look at the period, let's see, I'll do it in blue. There it is. That's the time it took to finish one cycle, or the length of the domain it took to finish one cycle of cosine is pi. And we knew that from the squeeze box theorem. So put this in your notes. You're gonna need this theorem. You're gonna use it over and over again. Let's see if I can get it in the screen where you can see the whole thing. There we go. I'll step out of the way, put that in your notes. You need that. We're gonna use it over and over again throughout the semester. Math made simple. It's Simpson Math.